speaker is Doug Pooler. Doug's from Hotstart, and he's going to speak to us about the system they have that helps keep diesel gensets hot and ready.
Thank you. My name is Doug Pooler. I've been a mechanical engineer for the past 30 years or so. The last 7 have been in product testing with Hotstart, looking at energy efficiency and ways that we can reduce power consumption for customers. So today I'll be talking about energy efficient engine heating for backup gensets. So why am I talking about internal combustion engines at an energy efficiency conference? So every backup gensets, internal combustion, HVO, diesel, natural gas engines are all very critical for, or very important part of critical infrastructure currently. They are been around for a while, and they are the standard as we speak, as long. Excuse me. Well, there are a lot of other new systems that are coming online. We're looking forward to the more efficient ones. These are, I am going to stand up here where my notes are, excuse me. So again, large genset production for the next 2 years is already completely committed from large genset manufacturers like Cat and Cummins. There are mostly due to demand from data centers, and so the demand for gensets is not decreasing. Well, we're all looking forward to alternative power sources being alternative power generation. For now, this is what we're working with, and they're going to be around for the next 20 to 30 years. So looking for ways to make them more efficient during their lifetime. So briefly what I'll be talking about today. First, I'm going to quantify the energy usage of backup gensets when they're not running, describe the measure that we're talking about in order to make them more efficient, and discuss how the data acquisition and modeling was done, review 3 of 11 case studies on this, as well as discuss the conclusions. And I understand that AEE will be distributing slides, so the other 8 case studies I'm not talking about, the slides for those are in the appendix. So if you're interested in that, you can look through the additional slides later. So most building owners or facility owners don't actually know how much energy their backup gensets are consuming on a day-to-day basis. I'd like to provide a little bit of context for that. NFPA 110 requires that all backup systems be able to provide power with full generator nameplate loading within 10 seconds. That is only accomplished when the engine is already warm, over 100 degrees Fahrenheit. In order to do that, the OEM has installed electric resistance heating on the engine. So that is constantly running, keeping it above 100 degrees Fahrenheit. You can see those. One of them's here, another, you can just see part of it there, and this is another heater. These heaters maintain the engine coolant temperature and circulate it throughout the coolant throughout the engine to maintain the temperature. We're talking here about saving 50 to 80% of the energy usage of those electric resistance engine heaters using an alternative engine heating process. NFPA also specifies how long emergency power must be available or must be able to be supplied. So for critical infrastructure, it also specifies the duration of fuel storage that must be on site. Hospitals require at least 96 hours of fuel storage on site so they can operate during an emergency situation for that long. Our local hospital has 7 days of fuel on site, and there isn't currently an alternative backup power system that can provide that with the reliability that they require for 7 days. There will be, but for now, this is what we have. Data centers, that's a big topic right now, so I'll address that briefly. The Uptime Institute suggests 12 hours of fuel reserves for a data center. Most data centers plan for 24 to 48 to 72 hours of fuel. This is a hyperscale data center. This is a hyperscale data center. You can see along this row of building, these are all, each individual box here is a 2.5 megawatt genset, and along this row of buildings, they're slightly different configuration and package, but those are also 2.5 megawatt gensets. So in that, this is a hyperscale data center in Boardman, Oregon. There are 4 more sites in this same area with similar layout. 2.5 megawatt gensets there, so 250 megawatts of backup or emergency power for 24 to 72 hours. So a significant amount of energy requirement there. And looking at discussing more about data centers, this is just a map where I've got it, just shown down the bottom, but we have currently around 122,000 megawatts in data center capacity, that it will be growing over the next 15 years. And if you assume just for some order of magnitude math, for every 2.5 megawatts of capacity, there is 1 backup genset. So a significant amount of gensets out there, significant amount of potential for energy savings. So we've already established that genset engines need to be heated. Typically that's with a 5 kilowatt and 12 kilowatt electric resistance engine heater. The most basic system is a tank on the outside of the engine with a hose going in from the bottom of the engine to the inlet of the tank, electric resistance element inside the tank, and then an outlet. As the element heats the coolant, it rises and goes to the top of the tank, so it's heated to near boiling for that to happen, and then cold coolant from the bottom of the tank comes back into the heater. The more energy efficient is to actually add a pump, because then instead of having to heat the water overheated essentially to near boiling, you only need to keep the engine around 100 degrees Fahrenheit. You can maintain the temperature engine at the set point that you want it to. So there's already, the Northwest Council Regional Technical Forum already has a prescriptive measure to replace thermal siphon or convective heating tank with pump-driven ones. We're looking at, what I'm talking about here is an alternate or another way to decrease this even further, and that's by adding an air source engine heater or air source heat pump in series with the electric resistance heater. That maintains the redundancy for installs or for customers, so that we're not replacing an OEM heater, we are adding something else in its place. This becomes a primary heater. The electric resistance heater is then called upon by the air source engine heater as necessary during when it gets colder and the COP of the air source engine heater is not adequate to heat the engine. The case studies will be just looking at various models of these air source engine heaters. You can see a couple of the engine heaters on the right here. The testing involved single speed air source engine heaters, and you can see the COP versus temperature there. The single speed did not have a defrost capability, so below about 45 degrees Fahrenheit, we were unable, it basically calls for the electric resistance engine heating as necessary. The alternate is a variable speed air source engine heater, and this was able to achieve a COP of about 2 at 5 degrees Fahrenheit. Now the cold weather heat pump standards of HSPF2 and SEER don't necessarily apply here, because instead of heating air to 70 degrees, as those standards are, we're heating coolant to over 100 degrees Fahrenheit. So slightly different application and requirements. Air source engine heaters in this testing were installed in a variety of locations. You can see some of them here, the variety of, we have an outdoor enclosure installation and another outdoor enclosure installation, vastly different, open louvers, closed louvers, basements. We have activated or active cooling within the room, active heating in some cases, different models electric resistance heating, as well as I mentioned, the basements with open louvers to the atmosphere, etc. So data was recorded either before the retrofit and after, typical pre and post, or with identical gensets in identical locations or identical enclosures. We recorded data concurrently for those. We recorded not only the energy usage of the engine, the OEM engine heater, but it's also the air source engine heater, and that way we could tell when the air source engine heater was requiring the electric resistance engine heat, and utilize various, I guess I'm not supposed to say CCS swap node, but I did. So anyway, various ways to record power consumption. This is an example of the data or the modeling that was done. The average kilowatts or kilowatt hours per hour consumed was modeled relative to outdoor temperature or indoor temperature, depending on where the best correlation was. And then if it was to indoor temperature, the relationship between room temperature and outdoor temperature was modeled as well. We downloaded hourly weather data from degreedays.net, and for the particular location, the nearest official weather station, and then for modeling for annual usage, utilize that same weather station in either TMY data as the facility required or historical data from a previous year. These are the 11 case studies that we looked at here. I'll only be talking about the 3 in green. As you can see, we utilized at least 3 months of data acquisition for each, both pre and post, or if it was concurrently. Engine sizes range from 1 megawatt gensets to 3 megawatt gensets, which was the equivalent of about 27 liter engine at the smallest for the 1 megawatt size to a 78 liter for the 3 megawatt. You can see that the variety of installations and locations were listed here, and I will get into the results of all of them at the end. I'd also like to thank Avista Utilities, which is a independent power or electric and gas utility in the Pacific Northwest. Levi Wester from there with the certification showing he did the analysis for that. He's actually written a white paper recently on this, so there will be a link to download that at the end if that is something that you're interested in. So again, I'm only going to be discussing the 3 in green. The first one, again, with this analysis conducted in cooperation with Avista Utilities, was a co-location data center. This was a concrete outbuilding, uninsulated, with open louvers to the environment for combustion air and cooling air during operation. Most gensets only operate during the 20-minute site or exercise once a month, and then if there's emergency power. So essentially the electric resistance heat is being utilized most of the time. This is shown in the model here, where the orange is the electric resistance engine heater, and its usage relative to outside temperature. The air source engine heater kilowatt consumption is shown at the bottom. So in this case, we had nearly 50,000 kilowatt hours per year that are consumed by the electric resistance engine heater. Nearly 12,000 was consumed on the same exact condition with the air source engine heater, for savings around 75%. There's multiple of these engines, and Avista Utilities did provide an incentive for this, and they retrofit multiple engines in this location. Second one I'll look at here is a district heating plant for correctional facility. In this case, there were 4 slightly smaller gensets within a large room. This room had active cooling when it was above 75 degrees Fahrenheit in the room, which basically meant they opened these louvers here, and fans on the wall above the engine's gensets started 4-foot diameter fans were pulling air into the room. That obviously affected this engine more than the 3 others to its left. So variation was shown or observed in that. They also had heating because they are a steam plant, so they don't care. So they did provide some heating, which you can see where it was essentially maintain the temperature, and then where the losses for the room were greater than the amount of heating that was able to be provided. So as we take, and I will say that the green line here is the weather temperature, so you can see how the room temperature changed relative to weather temperature. So you can see the variation in the 3 different baseline gensets. They each had different types of heaters, electric resistance engine heaters, from pump driven to thermosiphon. And then the one engine that was retrofit with a single speed air source engine heater. This is the energy usage for that. So as we look over the local weather, or apply that to the local weather in that location, energy savings were between 20,000 and 30,000 kilowatt hours per year, based upon the models for the 3 different engines. And again, incentive was provided by Vista for this location. The final one was in north central Oregon. In this case, this was 2 side-by-side outdoor enclosures with 2.5 megawatt, 2.25 megawatt gensets. Each of them had a 9 kilowatt electric resistance engine heater, and that was pump driven. You can see one of them had the single speed air source engine heater installed inside the enclosure. The other one was the baseline. You can see that the air source engine heater does reduce the temperature within that enclosure slightly, but the temperature is still above the outside air temperature. So if you're looking at the efficiency, if it was installed outside instead of inside, it would have operated more inefficiently because you benefit inside the enclosure from the higher temperature, which improves the COP. Data was recorded over a year, so we have more complete and model of this particular unit. You can see the essentially the curve that's more reminiscent of a heat pump than or what we expect from a heat pump than the linear curve fits that were in previous discussions or previous case studies. And then to this portion here is where, because it was a single speed air source engine heater with no defrost, it started requiring the electric resistance engine heater to heat the engine. You can see also that even when it's doing that, the amount of energy used to maintain the state of readiness of the engine was significantly less than the baseline where just the electric resistance engine heater was doing its job. So even at, it isn't until you get down to here where the 2 meet. So during the majority of the year in this location, there's a significant savings. It's only on probably the very coldest day. Engine savings, or electric kilowatt hour savings, were 21,700 for this location, about 66%. So if we summarize all the 11 case studies, and again, the other ones are available at the end of this appendix if you get the slides for this. We had range of savings from between around a little less than 17,000, 16,000, excuse me, to upwards of 57,000 kilowatt hours per year saved per genset, which this obviously, as the number of gensets increase for a location, this multiplies the ability or the savings for that facility significantly. You can see that even with the smaller size engines, the 27 liter, 32 liter engines, 1 megawatt genset, savings were still in the 70 to 80% range. However, because it's a smaller engine, smaller surface area, less convective loss to the environment around it, the total kilowatt hours for that engine that were consumed by the baseline and also saved were less, but it's still a 70 to 80% savings. again, that the analysis from Avista averaged around 22,450 kilowatt hours for their analysis, and the ones that we conducted averaged around 28,000 for the entire system. If you, just for trying to model this for future, to extrapolate it to other installations, if I just look at indoor installations over here on the left, and plot those energy savings relative to the engine liter size, you can see it, as you would expect, does increase, or savings increases with engine size, but there's a significant variation in that. And from some of the pictures, you can see some of that variation, but it basically involved, is the room heated or unheated? Is it a basement? Is it a small room? Is it a large room? All these things were found to be factors. There was actually more complexity in this than was expected during the initial study or investigation. So and there currently are more case studies going on that are in process, even on larger engines. So the goal of this is to be able to apply this to, or be able to come up with a comprehensive model that can take into account the size of the room, the size of the engine, what the particular variation is for that unique installation, and be able to come up with a good way to give that to the utility as a potential savings. So benefits of the air source engine heater: significant reduction of yearly kilowatt hour consumption, obviously. ROI can be from 2 to 5 years for smaller gensets. In order to achieve that, typically where the total kilowatt hours consumed by the baseline was less, typically that's only achievable with a utility incentive. As you can see, all the first 2 case studies that were talked about all had utility incentives, and every case study that was done by Vista did end up resulting in a utility incentive. There were also some of the other case studies also resulted in utility incentive. It was just with a different utility. Other benefits are due to the electric resistance engine heater no longer being the primary source of heat. The typical consumed or wear parts on that were no longer needing to be replaced, so that saves on maintenance for the facility, which can be significant. I've heard different numbers from different facilities. I won't say them here, but it can be a significant savings there. And this also can contribute to global or greenhouse gas and carbon reduction, depending upon the utility and their sources of electricity. Some of the challenges for an air source engine heater: if we just look at data centers, the amount of savings is relatively small for them. If we're looking at their power usage effectiveness, PUE, we're less than 0.2%. It does scale quickly. If you think back to that picture of the hyperscale data center that I showed earlier, there's a significant savings per site, but relative to the amount of energy usage for the data center for their IT loading and cooling loading, it doesn't look that big to them. Installation costs can affect ROI. Does the site specifically need hard piping, or are there requirements for specific engineering drawings? What does the AHJ have to say about something in this facility? And that can affect how much installation costs are. Contracted electrical rates can also be a significant challenge in some locations. Washington and Oregon, with a significant amount of hydropower, certain places have 4 cents per kilowatt hour, so it's difficult to get an ROI in a reasonable amount of time for those locations. But there is a growing network of installers with training that are available to install these. So briefly, internal combustion engines will be around for a while until alternate power generation methods that are developed that don't rely on internal combustion. Until then, we can save, I'll just average it at 25,000 kilowatt hours, somewhere between 50 and 80% of the electrical usage of the current or the baseline OEM installed electric resistance engine heater. There are custom and prescriptive measures either published or in development in the United States. Energy Trust of Oregon, currently it offers $22,000 per install of one of these. And there's continuing data collection ongoing at other sites in the US and worldwide, including larger 3 and 4 megawatt genset sizes, which will be up to 95 liters, or I think there's a 104 liter engine as well that we're going to be doing some data collection on. So I will be looking forward to continuing the modeling on this to be able to provide a better comprehensive model that can take into account the variation. So thank you very much for your time. As I mentioned, this is the location, or you're able to download the white paper from Avista Utilities from Levi Westra. Again, thanks to Levi Westra for his work on this project. And if you have any questions, I'd be happy to take them. Yes.
Do you ever run into doing any water source heat pumps? Like, you have water cooling available or geothermal?
We haven't run into that being available.
Okay.
There's the potential, obviously, for if you have a liquid cooled data center with water nearby, you have an easy source of power for that. Yes, but the infrastructure isn't necessarily there for that, and tapping into that infrastructure could be a challenge. So it would have to be essentially designed in as an original during the design of the data center and in the original installation or in the package with the genset. Yes.
Let me just maybe get clarity on something first. So the unit uses air to heat.
Yes.
So where is that air coming from? Is it compressed air?
No, it's just the surrounding air. So the air in the room or the air outside.
Okay.
Yes.
Any chance you left one of the models designed for extreme cold?
How extreme?
Minus 40.
-40?
Minus 80. That's minus 80 Celsius. Not so stable.
For a custom system, do you need UL and CE on it?
Yes.
Okay.
CSA.
Okay. That's something we can talk about from a custom side of things, but it is obviously the refrigerant, the size of the heat exchanger with the air change, the size of the compressor changes, and the programming changes there in order to make that possible, which means that it would be essentially idealized for that lower temperature and be very inefficient or may not work at all at the higher temperatures. So it's just that one of the kind of the limitations in some senses of the trying to account for the variation in weather as well as the limitations of refrigeration.
Okay. Yeah, that's right.
Though we can talk later.
Oh,
Yes.
so is the reasoning on the 100 degrees based on what the manufacturers say to get like full load right at the
Yes.
start? And then the reason to get full load right at the start is because of NFPA.
Yes.
So if a real world load is never going to even approach that, it's never even going to approach 50%, you still have to be able to provide 100%.
Yeah, so the generator has to, per NFPA, has to achieve that 100% nameplate loading on the genset. And you have, for a hospital, I don't know what their redundancy is, whether they're an N+1, maybe different places do it differently, or what. I know that the ones that I've visited, they don't have one genset for the entire facility. They have multiple small gensets that they can then use as loading is required for, once the neonatal region, once the OR, once the berthing center, et cetera. So
Yeah, and I guess because what I'm getting at is if the manufacturers of the engines say that you don't need to be at 100 degrees just to get started, but maybe you're not good for the nameplate rated load, but if you have multiple gens, you never run at the rated load, it's like 30%. You know, why would you even have to warm the water at all? Or can you lower it to 70 degrees or whatever?
So the other thing that you end up with is increased emissions when you're cold starting a diesel or an HBO or a natural gas engine. So the other reason that it is heated is for basically emissions, and then you're eliminating condensation. So if it's kept warmer than the room or the air temperature of the air around it, then you don't have the opportunity for condensation in your engine, which can cause corrosion and other issues too. So from a longevity standpoint for this 20 or 30 year asset, they maintain it at an elevated temperature for that reason. Even in UAE and the Middle East locations, they're still heated to an elevated temperature for those reasons.
Okay.
What about the application for diesel fire water pumps?
That is definitely an application as well, yes. And essentially any engine is, the issue is this: the engine gets smaller, the ROI becomes harder to achieve. It's definitely saves energy. It's just if you're accounting for when whatever the facility requires for a payback, it can be more difficult.
Thank you, Doug.
Thank you.
And thank all of you. We had great questions in all 4 sessions and a lot of interactions. So made my job very easy. I appreciate it.